So my name is Barry O'Reilly. I am a veteran architect. I've been working in the industry for over 25 years. I've previously been a chief architect at Microsoft. Currently I run my own company called Black Tulip Technology based in Sweden, where I do research, teaching and architecture consulting. Yes, Black Tulip is named after a character in one of Nassim Taleb's books called Skin in the Game. There's a character called Nero Tulip, and Nero is someone who understands the upside and downside of risk and how to be cautious in the face of systems that you don't properly understand. Oh, not really. So loose coupling is a very vague term that came about in the 1970s. It has its roots in the work of Ed Jordan and Larry Constantine, and it's become kind of a totem that we aim towards in software without really understanding why. And loose coupling means that components in our system aren't as coupled or aren't as tightly coupled to each other as they should be. And it was observed as far back as the 1960s that good architectures had components that were loosely coupled to each other. Now the question that architecture hasn't been able to answer since then is what level of coupling should exist between which components. And so we've ended up doing all kinds of rituals and guesswork and memes that tell us how to loosely couple our architectures, but it doesn't actually work. Rarely works. What residuality does is it teases out where should that coupling be, how should components be connected to each other, and we use the context of the actual business environment and we use human narrative to capture that. So I'm not sure if they knew each other. So Gall's Law, I think you mean the one where we say that every complex system has evolved from a simple system. I'm not a big fan of Gall's Law. I think it's obvious that every complex system has evolved from a simple system. In the software industry, we've interpreted that to mean that my simple system is good because it's going to evolve into a complex system. Or I don't need to think, I just need to write a few lines of code. That's the simple system that's going to evolve into the complex system. Stop trying to make me think. And I see Gall's Law used as a get-out clause from thinking in the software industry. It depends on who you are. So we're talking to a technical audience now. So I'm assuming that you're a technical person with a very technical background with a STEM education and some years writing code. And one of the things that people struggle with is that when we look at a system and we say, what could stress this system? And stress in my world means model stress. What is outside of my current understanding of this system? What could happen that I'm not aware of yet? When technical people look at this, they think about technical stress. They look about disk failures and network failures and all these kind of things that we've been working with right through our careers. But model stress can also be things like, what does a competitor do? How does a competitor behave? How do our customers actually feel about us? And what if that changed? How do our employees feel about working here? All of these kind of things are stress on our system. And technical people can feel quite intimidated. They can feel like it's quite difficult to come up with these kind of stressors. And part of the reason for that is that we've been patronized for generations by business people who said, don't worry your pretty little technical heads about this. This is too much for you. We do, It turns out that all it really takes is half a day of learning some simple business tools, things like Porter's 5 forces or Miles and Snow typologies or pestle analysis, to be able to start stressing a business system so that you can actually interpret how will this code structure behave as flux is introduced into the business system. The biggest thing that technical people can do to improve at this is to lift your own confidence, to believe that you can actually do this, because what I see that stops people, that puts the brakes on, is a lack of belief in their ability to do this. Anyone can do this. It's not very difficult. So threat modeling is one of a bunch of different techniques that people look at and think, is this similar? Threat modeling, chaos engineering, risk management, ATAM scenario analysis, edge case analysis, all of these kind of things. And people get this mixed up with the stressor analysis because the motion feels the same. We see an event, it has an effect on our system that's negative, and we want to mitigate that effect. The huge difference with residuality is that the events themselves are irrelevant, and the probability of that event happening is irrelevant. So when you generate a standard risk analysis or a threat model or something, we tend to organize and filter all the data that's generated in that by probability and by impact. And when we use probability, what we're saying is we don't have time to address everything that we're going to work with. And probability is a number we make up, right? There's nothing scientific behind it. We just pull numbers out of the air to make ourselves feel like we're doing something scientifically credible. And those numbers, those probabilities, reflect nothing more than the bias of the people in the room about what's likely to happen. In residuality, we say that your picture of what's likely is going to lead you astray. Your belief that you can predict what's going to happen in the future of a complex system is dangerous to your ability to model and build that system. So residuality gets rid of that. And what we say is everything has a probability of 1. And that's a radical departure from any form of risk analysis or threat modeling that we do. So these things have something in common, and I would expect most of those tools to produce a very small subset of what residuality produces. And what residuality does is it trains our architecture, it pulls it into a particular shape. And once we have that shape, then we can test it and verify that it actually holds up against unexpected sources of stress. Once we're done with that, we throw away all of those stressors. They're noise and nonsense and speculation. With risk management, once you pull those things in, or threat modeling, then they're real. You have to react to them, you have to mitigate them. In this case, we're trying to move our architecture to the point of criticality. So one-to-one mitigation is not the goal. With all of those other tools, one-to-one point prediction and one-to-one mitigation is the rule. And that's standard traditional engineering, which doesn't hold up in complex systems. When I'm teaching architecture, I tell architects that we are all unique. There is no such thing as an architectural process that applies across many different architects. All of us are forged in the fires of our careers and the luck and the chance and all the randomness that throws us into different projects. So when you, as an architect, listen to residuality, you're going to take different things home than the people sitting beside you. The immediate things that I want people to take home from a residuality talk or a quick skim of the book is, 1, you cannot predict the future. You do not know what is going to happen. And a follow on from that, which is very obvious but needs to be said, you don't know what's not going to happen in a complex system. So forget about your yagni and allowing your biases to override these kind of things. You do not know what the future holds. When you have to make decisions about the modularity of a software system, about the design of that software system and the relationship between its components, you necessarily have to think about the future of a complex system which you cannot predict. And every architectural tool that you use, traditional architectural tools, are deeply, deeply flawed because they hide from this problem and they actually exacerbate it and make it worse. If you bring that home with you, that will start to change your practice. And if you think about it long and hard enough and you start trying to solve this problem, you will eventually arrive at something that looks very close to residuality theory. If you want to go faster in that learning cycle, then read the book or take the course. Yeah, this has been a great conference. It's fantastic to come back to an architecture conference. For the last 2 years, my focus has been on developer conferences because one of the things we've discovered about residuality is that it has real appeal to senior developers who've maybe become a little bit disillusioned with architecture as it has been practiced, and especially enterprise architecture in the last few decades. So I've been focusing on those conferences, and coming to something like the Software Architecture Gathering here in Berlin has felt like a coming home to an audience of architects who are fighting the same battles that I've been fighting for the last 25 years, and it's incredible to see the enthusiasm for the ideas that I've been talking about. What's even more incredible is to see the recognition, that little glint in the eye of the senior architect who says, this is what I've been trying to tell people for the last 20 years. This is how it actually works. And so, yeah, it feels like coming home, and it's been a fantastic conference, a fantastic atmosphere. Great to see so many old friends, and great to bring these ideas to Germany and to Berlin.